What's up, you guys? Geometry Module 3, Topic 1, Lesson 3. We're on page 475. To be prepared for this one, have a highlighter, have some tracing paper, have a protractor, and of course, have page 474 done. If you haven't done that video yet or don't have the access to those notes, go get them. Get that done, stop, go back and watch that one. Now, I'm going to go ahead and share with you that there's some pre-writing that I did before the video started, and it is to at least give me some sentence stems. So pause right here, write those sentence stems out, and then we're going to write them together and finish them out. I'll also show you the bottom half of the page. Okay, so pause, and you're back. And then this is the bottom of the page as well. So I want to give you those sentence stems before we begin. So pause, and we're back. Now, in this question 3, right? Question 3 at the top of the page. Use a ruler to compare the lengths of the line segments connecting the marbles on the first row, so highlighted in yellow, to the length of the line segments connecting the marbles on the second row, which I highlighted in blue. If you remember, I measured this distance, and then I measured that using that information. I measured this one. It turns out that whatever this original pre-image distance was, by dilating it by double, I made the new distance be twice the length, right? So the line segments connecting the marbles on the second row are twice the length of the line segments on the first row. I'll say to the marbles on the first row. That's what a dilation does. A dilation will allow us to grow or stretch or shrink, but the scale factor is specifically related to distances. What is the change in distance of a line segment stretched out from the center of the dilation? And it's a scale factor that does it. So, scale factor has been one of our key words here. What can you conclude about dilating a line that does not pass through the center of dilation? What I mean for that question is how blue is formed. And if yellow was the original line and it's not passing through the center of dilation, it is off of that amount. Well, the blue line is what happens when we dilate. We are pushing, like expanding out the line, and it happens to remain parallel line. So these lines that don't touch the center of dilation will be pushed parallel away from the center of dilation, or pulled into if we're doing a contraction. Consider the line AB. How could you show a dilation of this line using point P as the center of dilation? Well, here's the deal. If we're going to talk about a dilation, then we should draw the ray that is used. Like dilations have rays like a sun expanding from them. So we're going to dilate P, this ray in that direction. We're going to dilate P in the other direction. And the reason why I don't turn and tilt it through any other point is because that line is already guiding us from A to A double prime and from B to B prime. What happens when the line is dilated through the center P such that point P is dilated? So we're going to move like this amount. Let's move to an identical line. We actually didn't change anything, right? Case in point is this. Here is P, here is B, here's B prime, and we're taking this line and it's the same one. There was no change as we moved this. So we're going to take the line to an identical line. Okay, let's try the next one. What happens to the line when the line is dilated through center point P such that A is dilated to A prime? Or single right there, right? Okay, so when that happens, what's happening is the exact same thing. If the point and the center of dilation create a line segment or create a ray, then any sort of like movement along that line will still be on that line. So the same thing. We're going to take the dilation to an identical line. Okay, what can you conclude about dilating a line passing through the center of dilation? Dilating a line passing through the center of dilation will take the line to an identical line. That is always the case. with lines that go through the dilation. You're actually not stretching or moving, you're just moving it, but it's not visibly moving because lines go infinitely in both directions. Takes the lines to identical lines. Parallel. No, not even parallel, just identical. It's the same location. Okay. That's been page 475. Next up on our list is 476, which launches activity 2. So in activity 2, we'll talk about this poster right here, angle bisector and the proportional sides theorem. Thanks for watching this episode. Like, comment, and subscribe, and click on the next video where we talk about angle bisectors and proportional sides, and I'll see you on the next episode.